My name is Santosh and I am a student of Chemistry Honours first year. Here I want to discuss a topic named soil and water analysis. Mainly here we will discuss the complexometric titrations, their basics. So here I'll start. First is the composition of soil. Components of soil are mineral, organic matter, water, and air. Mineral are about 45%, organic matter is about 5%, water is 20 to 30%, and air is also 20 to 30%. pH measurement of soil. The pH measurement of soil is done with the help of pH meter. The steps are: the pH meter is calibrated using pH buffer solution. Then the pH meter is adjusted with known pH of buffer solution, that is 4.0 or 9.2. 5 gram soil is weighted and transferred into 100 ml beaker. 50 ml distilled water is added and stirred well with a glass rod. This is allowed to stand for half an hour with intermittent stirring. To the soil water suspension in the beaker, the electrode is immersed and pH value is determined from the automatic display of pH meter. Now, complexometric titrations basics. Metal ions react with electron pair donors to form complex ions, and the donor species are known as the ligands. A ligand which has only a single donor group, for example H2O, NH3, are known as unidentate ligands, whereas the ligands which have two or more than two groups to donate are known as polydentate ligands. For example, ethylene diamine is a bidentate ligand. Also, glycine is a bidentate ligand. Whereas ethylene diamine tetraacetic acid, which is EDTA, is a hexadentate ligand. Unidentate and few bidentate ligands do not complete the complexation reaction. This is because in the formation of complex with such ligands, more than one ligand has to be added to satisfy the coordination number of the metal ion. For example, if AgNH3 twice whole positive complex is formed, then in the formation AgNH3 whole positive ion will also persist. Or we can say in the moderate concentration of NH3, AgNH3 whole positive will exist. So, to complete the coordination number, required amount of unidentate ligand is necessary. However, polydentate ligands are generally form 1:1 ratio complexes with the central metal ion. Reaction takes place in one step without the formation of the intermediate species. The quick, complete and one-step interaction of polydentate ligands with the metal ions to give stable complexes is the basis of the complexometric titrations. EDTA is commonly used in the complexometric titrations, commercially available under the names such as Versone, Trilone B, Sequestrine, Complexone, etc. Chelation. Chelates are cyclic compounds that are formed when a ligand binds the central metal atom ion through two or more donor atoms of a ligand. Such a ligand which binds the central metal atom through two atoms is called a chelating ligand, and the process is known as chelation. Chelated complex formed by multidentate ligands such as ethylene diamine, acetyl acetonate ion or EDTA have been found to be more stable than those formed by the monodentate ligands such as H2O, NH3, pyridine, etc. This increase the stability of the complex containing chelating ligand is called chelate effect. For example, if we use a monodentate ligand, then there will be no increase in the entropy in the product side. Whereas when we use a polydentate ligand, which is either a bidentate ligand or a hexadentate ligand, for example EDTA, then entropy will increase in the product side. Thus, increase in the number of the molecule decrease the order of the system and increase in the entropy of the system that is responsible for the stability of the system. Complexometric titrations, the quick, complete, and one-step interaction of the polydentate ligands with the metal to yield stable complexes, is the basis of the present day complexometric titrations, in which metal ion solutions are titrated against solutions of polydentate ligands. EDTA titrations. Ethylene diamine tetraacetate acid, that is EDTA, as well as its sodium salt, used due to its solubility in the aqueous solution. It forms stable water soluble, that is 1:1 ratio complexes with most of the polyvalent ions. EDTA has a cage-like structure and it has 6 donor sites, 2 are nitrogen and 4 are oxygen. EDTA is a tetraprotic acid and it is usually written as H4Y. The dissociation constant for the 4 COH groups are K1 is equals to 1 into 10 raised to power minus 2, K2 is 2.15 into 10 raised to power minus 3, K3 is 6.95 into 10 raised to power minus 7, and K4 is 5.5 into 10 raised to power minus 11. From the dissociation constant, it is observed that pH greater than 12, the EDTA exists as Y4 negative, whereas at pH is equals to 8, EDTA exists as HY3 negative, and at pH 5, EDTA exists as H2Y2 negative. Most of the EDTA titrations are carried out in neutral or alkaline solution, in which predominant species are H2Y2 negative and HY3 negative. For example, M2 positive plus H4Y give rise to MH2Y plus 2H positive. To carry out the reaction in a basic buffer solution, removes H positive as it is formed, which favors the formation of the EDTA metal cation complex reaction product. Indicators for EDTA titrations. Organic dyes are used as indicators in the EDTA titrations. These dyes form complexes with metal ions which are intensely colored. The formation of metal indicator complex occurs in a specific range of the concentration of the metal ion. This range is characteristics of metal ion and the indicator used. The most widely used indicator in these titrations is the Erichrome black tea, which is black in color in the unionized form, whereas Erichrome black tea in aqueous medium and the ionized form will be red in color. The SO3H group of the indicator gets ionized in aqueous medium, giving an anion which has a red color. Indicator H3ion represented. H3ion, which is black in color, plus H2O gives rise to H3O positive plus H2 and negative, red in color. H2 ion negative plus H2O give rise to H3O positive plus HIN2 negative, that is blue in color, and HIN2 negative plus H2O give rise to H3O positive plus IN3 negative, that is orange in color. Both these reactions in solution have pH greater than 7. It is observed that indicator would exhibit different colors depends upon the pH values. The free indicator HIN2 negative liberated in the endpoint reaction would be blue in color since the pH of the buffer is around 10. Thus, a change in color from red to blue marks the approach of the endpoint. EDTA titration methods are as follows. First is the direct titration. In this method, standard solution of EDTA is slowly added to the metal ion solution till the endpoint is achieved. Second one is the back titration. The reaction of metal ion with EDTA is slow. The metal ion precipitates. No suitable indicator is available, then this type of titration are applicable. In this method, an excess of standard solution of EDTA is added to the metal solution being determined so as to complex all the metal ions present in the solution. The excess of EDTA left after the complex formation with metal is back titrated with the standard solution of a second metal ion. Usually standard metal ion solution used are ZnCl2, ZnSO4 and MgCl2. The third one are the displacement titrations. When direct or back titrations do not give result, then displacement titrations will take place. The metal to be analyzed is added to a metal EDTA complex. The analyte ion displaces metal from the EDTA and metal is subsequently titrated with the standard EDTA. For example, in the determination of manganese, an excess of magnesium EDTA chelate is added to the manganese solution. The manganese ions quantitatively displacing magnesium from the magnesium EDTA solution because manganese forms more stable complex with EDTA. Mn positive plus Mgy2 negative give rise to MnY3 negative plus Mg2 positive. The free magnesium metal is then titrated direct with the standard solution of EDTA using Erichrome black tea indicator. And the last but not the least, fourth is the indirect titrations. Certain anions that form PPT with metal cations and do not react with the EDTA can be analyzed directly. For example, sulfate ions can be determined by adding excess of barium 2 positive to pipette out as BaSO4. The precipitate is filtered and washed. The excess of barium 2 positive in the filtrate is then titrated with EDT. And this is how the topic of complexometric titrations end up.